When the interstellar object designated 3I/Atlas was initially discovered, astronomers assumed they were observing something small, delicate, and fairly straightforward to explain. It seemed like a routine visitor from another star system, a fast traveler briefly crossing our solar neighborhood before vanishing into deep space. But that explanation didn't hold for long. As the James Webb Space Telescope and other observatories kept tracking 3I/Atlas, the incoming data began to shift. And with that shift, the original narrative started to fall apart. The object wasn't acting the way it was supposed to. Its chemistry defied expectations. Its motion didn't align with predictions. And now, the most unsettling discovery yet has surfaced. 3I/Atlas is far larger than anyone anticipated, so large that many of its strange behaviors shouldn't even be possible. Its size, composition, trajectory, and classification no longer fit together. Instead of resolving questions, the newest images have introduced contradictions. And in astronomy, when contradictions accumulate, it usually signals one thing: we are facing something we don't yet understand. Following detailed post-perihelion observations, astronomers were finally able to directly image the nucleus of 3I/Atlas with enough precision to estimate its true dimensions. Using data gathered between December 2025 and January 2026, researchers inferred a diameter of roughly 2.6 kilometers, with an uncertainty of about 400 meters. That places the object somewhere between 2.2 and 3 kilometers wide. At first glance, that might not seem dramatic, but in astronomical terms, it completely reshapes the story. Only a month earlier, most estimates placed 3I/Atlas at around 1 kilometer in diameter. Because mass scales with the cube of the diameter, this revised measurement doesn't mean the object is merely 2 or 3 times more massive. It suggests it's closer to 27 times more massive than previously thought. Compared to 2I/Borisov, the only other confirmed interstellar comet studied in detail, 3I/Atlas is roughly 40 times more massive. It was never truly small. It only appeared that way because its nucleus remained hidden until the right instruments and conditions revealed it. This updated size immediately clashes with many earlier observations. When 3I/Atlas made its closest approach to the Sun on October 29, 2025, it displayed a noticeable asymmetry in activity. Leading up to perihelion, its brightness steadily increased. Afterward, it dimmed much more quickly, and its surface brightness profile became significantly shallower, suggesting its activity subsided rapidly. Meanwhile, the nucleus light curve revealed temporal variations, a pulsing pattern possibly linked to rotation. Yet the pulsing occurred far faster than the inferred rotation period would suggest. All of this was already unusual. But once the true size of the nucleus was established, explaining it became even harder. A large, massive body should not react so dramatically to solar heating, nor should it show rapid brightness fluctuations typical of much smaller objects. This peer-reviewed size estimate directly contradicts earlier assumptions and deepens the mystery. If 3I/Atlas is truly this large, then many of its subsequent behaviors should have been impossible. After perihelion, the James Webb Space Telescope conducted the first infrared spectroscopic analysis of the object at heliocentric distances of approximately 2.2 and 2.54 astronomical units. What emerged from the data shattered prior expectations. The chemical composition of the coma shifted dramatically. Water vapor began dominating far more than before, while carbon dioxide, once abundant pre-perihelion, declined significantly. That reversal alone was unusual, but it was only the beginning. Nickel continued appearing in surprisingly high quantities, something already considered strange, and now iron was detected as well, despite being absent in earlier readings. When scientists calculated the nickel-to-iron ratio, the result was extreme, far outside the range observed in any known comet within our solar system. The study pointed out that such high nickel concentrations have previously been associated mainly with industrial processes, not natural cometary activity, though natural explanations can't be entirely ruled out. Even more troubling was the timing. These chemical shifts occurred only after perihelion, suggesting that material inside the nucleus was being exposed in a sequence inconsistent with known sublimation patterns. Then came the most perplexing finding. Methane appeared, not in trace amounts, but in substantial quantities, reaching between 13.7 and 27% of the water production rate during 2 observation periods. This is where the chemistry truly stops making sense. Methane is hypervolatile, meaning it sublimates at lower temperatures than either carbon dioxide or water. If it existed in the outer layers of 3I/Atlas, it should have been detected early, especially as the object approached the sun. It should have appeared before carbon dioxide dominated the coma. Instead, methane was completely absent in earlier observations, even while carbon dioxide and carbon monoxide were clearly present. Stranger still, methane production increased as the object moved farther from the sun, the exact opposite of what standard cometary physics predicts. One proposed explanation suggested methane was depleted in the outer layers and exposed only later as sublimation progressed. But this idea falls apart because carbon monoxide, more volatile than methane, was detected early on. If methane had been there, it should not have been missing. The observed sequence was carbon dioxide and carbon monoxide first, then abundant water, and only later methane appearing and increasing with distance. The study states plainly, no current natural explanation fully accounts for this behavior. The chemistry of 3I/Atlas does not match any comet we've studied, whether from our solar system or beyond. Rather than resolving the mystery, the chemical evidence intensifies it. Its motion raised concerns as well. From the moment 3I/Atlas passed perihelion, astronomers noticed that its trajectory wasn't purely gravitational. There was an additional component, a measurable shift in speed and direction that gravity alone couldn't explain. Non-gravitational acceleration isn't unusual in comets. Gas jets can act like tiny thrusters, creating subtle rocket-like effects. However, the critical issue is this. Models that reproduce the observed acceleration all assume a nucleus roughly 1 kilometer or smaller in diameter. Detailed studies cited in the paper suggest diameters between about 820 meters and 1.5 kilometers are consistent with the required mass loss. Those sizes correspond to an object with only a fraction, roughly 1/27th, of the mass we now know 3I/Atlas possesses. In simple terms, its motion makes sense only if it's lightweight, and we now know it isn't. With the revised 2.6 kilometer diameter, the problem becomes severe. An object that massive should be extremely resistant to acceleration. To produce the observed trajectory changes, it would require unrealistically intense mass loss, far beyond what typical cometary outgassing can provide. While some of the trajectory shift can be attributed to gravitational effects during its close solar encounter, a significant portion cannot. That remaining acceleration would demand explosive outgassing on a scale never observed, or a surface area far greater than data supports. This is why the discrepancy matters. Behavior that once seemed plausible under the assumption of a small object becomes deeply problematic once its true mass is considered. 3I/Atlas altered its course in a way small bodies can, but large ones should not. While this doesn't prove anything exotic, it pushes the object beyond the comfortable limits of existing models. Size, motion, and physics are no longer in agreement. And when the equations refuse to balance, astronomers must acknowledge that something fundamental remains unresolved. Comparisons with previous interstellar visitors only heighten the anomaly. Oumuamua was small and oddly shaped. 2I/Borisov behaved more like a conventional comet, though from another star system. But 3I/Atlas stands apart from both. With a diameter between 2.2 and 3 kilometers, it is dramatically larger than either predecessor. Here's the statistical puzzle. If objects like 3I/Atlas exist, then far smaller ones should be vastly more common. Yet we didn't detect dozens of Oumuamua-sized bodies or Borisov-like comets before encountering something this massive. The study emphasizes how counterintuitive that is. Discovering such a large object without first identifying a population of smaller ones suggests either an observational bias we don't yet grasp, or that 3I/Atlas belongs to an entirely different population. As these anomalies accumulate, the paper reaches a cautious but unsettling conclusion. 3I/Atlas does not behave like a comet as we currently define comets. Its chemistry is inconsistent. Its size defies expectations. Its motion doesn't align with theory. Yet there is no direct evidence it is artificial. Instead, a subtler possibility emerges. 3I/Atlas may represent a type of interstellar object never before encountered, formed under conditions unlike those of our solar system, carrying materials and structures that challenge our classifications. As more interstellar objects are observed in the coming years, this uniqueness may become clearer. 3I/Atlas could stand not as an anomaly to dismiss, but as the prototype of a new category. Even after it leaves our solar system forever, its data will continue to be analyzed because it compels us to reconsider what travels between stars. James Webb didn't simply deliver sharper images of a strange visitor. It exposed the limits of our frameworks. It revealed a problem: numbers that don't align, chemistry that breaks expected patterns, motion inconsistent with known mass. 3I/Atlas is far larger than predicted, yet it behaved like something much smaller. It released elements in the wrong order, at unexpected times, in unusual proportions. Methane appeared when it shouldn't have. Nickel persisted where it didn't belong. Volatility trends reversed with distance from the sun, placed alongside its trajectory changes that imply a lightweight body. The contradiction becomes impossible to ignore. This does not mean 3I/Atlas is artificial. The study is explicit about that. But it also makes something else clear. This object does not fit comfortably within our existing understanding of comets, asteroids, or interstellar debris. It is too large, too chemically unusual, and too dynamically inconsistent to be neatly explained by current models. Perhaps that's the most unsettling realization. Not that we found something extraordinary, but that the universe has quietly reminded us how little we truly know about what drifts between stars. 3I/Atlas may be unique, or it may be the first glimpse of an entire class of objects we previously lacked the tools to detect. Before vanishing back into interstellar space, James Webb provided one final gift: clarity. Not answers, but clarity that our assumptions were incomplete. In the years ahead, 3I/Atlas may mark a turning point. The moment astronomers recognize that interstellar space holds more than familiar remnants of planetary systems like our own. Whatever 3I/Atlas ultimately proves to be, it has already accomplished something remarkable. It has forced us to expand the boundaries of what we consider possible. Now I want to hear from you. Do you see 3I/Atlas as a rare outlier, or the first sign of a new class of interstellar objects we're only beginning to recognize? Share your thoughts in the comments. And if you want to stay at the forefront of discoveries like this, don't forget to like, subscribe, and stay curious, because space clearly isn't finished surprising us. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.